In 1950, at a lunch table in Los Alamos, New Mexico, physicist Enrico Fermi paused a conversation about comic strips and nuclear research to ask 4 words no one has answered since. Where is everybody? He wasn't wondering about late colleagues. He was looking at the numbers, hundreds of billions of stars in the Milky Way alone, many far older than our Sun, most now confirmed to host planets of their own. By every reasonable estimate, civilizations should have risen across this galaxy long before ours. They should have built, explored, left something we could notice from afar. And yet every instrument we have ever pointed at the sky has returned the same thing. Silence. A quiet so steady it almost feels like it means something. That silence is where tonight begins. Not with answers, there may not be any we can hold with certainty, but with the question and the weight of all that quiet pressing down around it. When civilizations rise and quietly fade, they do not always leave ruins or signals. Sometimes they leave only absence. And absence, as it turns out, has a texture of its own. We will follow 3 threads through that absence tonight. First, the staggering scale of possibility, the billions of worlds where conditions may have once been right. Then the chain of barriers, some perhaps already behind us, some perhaps still waiting ahead, that might explain why the galaxy appears so still. And finally, what that stillness might mean for one small civilization sitting on a blue planet, listening to stars that do not speak back. There is a way of understanding this puzzle that scientists sometimes call the Great Filter. The name is unassuming. It sounds more like a kitchen appliance than a theory about the fate of species. But the idea it carries is unsettling in the gentlest way. Somewhere along the path from raw chemistry to a civilization capable of reaching the stars, there may be steps so difficult, so unlikely that almost no one passes through them. These steps are the filters. And if we accept that the galaxy should be alive with voices, but hear nothing, then the implication is quiet but clear. Most who attempt the journey may not make it to the end. The question is where those filters lie. Consider the very first step, the leap from lifeless molecules to a living cell. We still do not know exactly how it happened on Earth. Experiments have shown that amino acids, the building blocks of proteins, can form under the right conditions. Lightning heat, the chemistry of ancient oceans. But moving from those building blocks to a self-replicating system, something that copies itself, stores information, creates order from the chaos, that remains one of the deepest mysteries in science. If that step is nearly impossible, then perhaps life itself is the rarest thing in the universe, and the silence above us is simply what an empty galaxy sounds like. But here is what makes it strange. On Earth, life appeared remarkably quickly. Geological evidence suggests that the first microorganisms were already present not long after the planet cooled enough for oceans to form within a few 100 million years of Earth's birth. If the origin of life were truly a 1 in a trillion accident, why did it happen so fast here? That speed has led some researchers to suspect the first filter may not be as hard as it seems, which means the harder barriers might sit elsewhere, further up the chain, closer to where we stand now. For nearly 2 billion years after life appeared, Earth remained a world of microbes. Nothing more, no eyes, no limbs, no nervous systems, just single cells drifting through ancient seas. 2 billion years is a span almost impossible to feel longer than the entire history of complex life that followed it. The leap from those solitary cells to multicellular organisms, creatures whose cells cooperate, specialize, and trust one another enough to form a body, may have been one of the most difficult transitions biology has ever managed. On Earth, only a handful of lineages crossed that threshold. Plants, fungi, animals, everything else stayed small. And even once complexity arrived, intelligence was anything but guaranteed. Dinosaurs dominated this planet for 150 million years. They adapted to every climate, grew to extraordinary sizes, filled almost every ecological niche. Yet in all that time, not one of them built a fire or carved a symbol into stone. Intelligence, at least the kind that builds telescopes and wonders about the stars, appears to be a strategy that evolution stumbles upon rarely, if at all. It took a specific chain of accidents to produce us, including an asteroid strike 66 million years ago that cleared the stage for mammals in the first place. Remove that single event and the story of Earth might still belong to creatures who never once looked up and asked a question. So perhaps the filters are already behind us. Perhaps the silence of the universe means not that civilizations destroy themselves, but that they almost never arise. Perhaps Earth is extraordinary not because it has water or warmth, but because an almost impossible sequence of events unfolded here, one after another, across billions of years, and somehow none of them broke the chain. But there is another possibility, and it is the one that lingers. Maybe the hardest barriers are not in the past. Maybe they wait ahead, because once a civilization gains enough power to reshape its world, it also gains enough power to break it. Nuclear weapons have existed for less than a century, and already they have brought humanity to the edge more than once. Climate systems that took millions of years to stabilize are shifting under the weight of a few hundred years of industry. Technologies we are only beginning to understand, artificial intelligence, gene editing, synthetic biology, carry promise and peril in equal measure. If civilizations elsewhere followed a similar arc, rising and innovating and then pressing too hard against limits they did not fully understand, then perhaps the silence is not a sign of emptiness at all. Perhaps it is the sound of sparks that burned brightly for a moment and then quietly went out. We do not know which story is true. We may never know. The silence does not explain itself. It only sits there vast and patient while we try to read meaning into the spaces between the stars. What we do know is that the question matters not because it tells us about distant civilizations, but because it turns us back toward ourselves, toward the fragility of our own systems, toward the choices we have not yet made, toward the small, finite world beneath us that holds, as far as anyone can tell, the only minds in the galaxy capable of wondering about any of this at all. And so, with that quiet pressing gently around us, we step back to where the story begins, 4 billion years ago, on a young Earth still cooling from its birth, where something in the chemistry of an ancient ocean crossed a line that no one has fully explained since. The first crossing. 4 billion years ago, Earth had no continents as we would recognize them. The surface was mostly dark ocean, broken here and there by volcanic islands venting sulfur and heat into an atmosphere with almost no free oxygen. The sky would have appeared hazy, tinged with orange and grey, heavy with carbon dioxide and methane. Beneath that foreign sky, the oceans were warm. Some estimates suggest surface temperatures may have hovered around 50 degrees Celsius in places, and rich with dissolved minerals carried up from hydrothermal vents deep below the seafloor. It was not a gentle world, and yet it was in this world that something happened which no experiment has fully recreated since. Somewhere in that chemical murk, molecules began doing something unusual. Not life, not yet, but the precursors of it. Simple organic compounds, amino acids, lipids, nucleotides formed and broke apart and reformed, driven by energy from lightning, ultraviolet light, and the heat of volcanic systems. In 1953, a graduate student named Stanley Miller, working in Harold Urey's laboratory at the University of Chicago, sealed a mixture of gases, or thought to resemble Earth's early atmosphere, inside a glass flask, sent electrical sparks through it to simulate lightning, and waited. Within days, the flask contained amino acids, the building blocks of proteins. The results stunned the scientific community. It suggested that the raw ingredients of life could form easily, almost eagerly given the right conditions. And that small detail has never quite settled into a comfortable explanation, because forming the ingredients is not the same as building the house. The distance between a collection of amino acids and a living cell is enormous. A cell requires a membrane to hold itself together, a genetic system to store and copy information, and a metabolic process to harvest energy. On modern Earth, these functions are handled by intricate molecular machinery, DNA, RNA, proteins, enzymes, all working in concert. But which came first? You cannot have proteins without the genetic code that instructs their assembly, and you cannot copy the genetic code without the proteins that do the copying. It is a loop with no obvious starting point. One hypothesis that has gained traction over the past few decades is the RNA world. RNA, a molecule closely related to DNA, can both store genetic information and catalyze chemical reactions, a dual role that might have allowed it to serve as the first self-replicating system before DNA and proteins took over. In laboratory settings, researchers have coaxed short RNA strands to copy themselves under certain conditions. But certain conditions is doing a great deal of work in that sentence. The environments required are narrow, the copying imprecise, and the leap from a self-replicating molecule in a test tube to a functioning cell in a primordial ocean. This remains one of the widest gaps in our understanding of biology. What makes this gap so significant for the question of cosmic silence is its uncertainty. If the origin of life was relatively easy, if it happens wherever water, warmth, and chemistry come together, then microbes may be scattered across billions of worlds. The galaxy could be rich with biology at the simplest level. But if the origin of life was an almost impossible accident, a convergence of conditions so specific that it has only happened once in 13 billion years, then the silence of the stars needs no further explanation. We would be alone not because civilizations destroy themselves, but because life itself almost never begins. The geological record on Earth offers a clue, though not a conclusive one. The oldest confirmed microfossils date to roughly 3.5 billion years ago, structures found in rock formations in Western Australia's Pilbara region that bear the signatures of ancient microbial communities. Chemical traces in even older rocks, some dating to nearly 4 billion years, suggest that biology may have been present almost as soon as Earth's surface cooled enough for liquid water to persist. That speed is striking. The planet had barely settled and already something was alive in it. Some researchers interpret this as evidence that life arises easily, that the chemistry of water and carbon is so inclined towards self-organization that biology is almost inevitable once the stage is set. Others caution that we are reading our own history through a distorted lens. We can only observe life's origin on the one planet where we know it succeeded. There may be billions of worlds where the same chemistry was present and nothing ever crossed the line. Our early start might not reflect ease at all. It might reflect the fact that we can only ask the question from a place where the answer already happened to be yes. This is what scientists sometimes call the anthropic bias, and it is one of the quieter frustrations of astrobiology. Every conclusion we draw about the likelihood of life is shaped by the fact that we are alive to draw it. We cannot visit the planets where chemistry remained chemistry. We cannot count the oceans where amino acids drifted for billions of years without ever assembling into anything that could reproduce. All we have is Earth. One example, one success, and no way to know how many failures surround it. Still, the speed of life's appearance here is difficult to dismiss entirely. If the origin of life were truly a 1 in a trillion event, you might expect it to have taken longer, to have required billions of years of failed attempts before finally crossing the threshold. The fact that it seems to have happened within a few 100 million years of Earth's formation at least suggests that the barrier, while real, may not be the highest one in the chain. And if that's the case, then the great filter to the step that stops most paths from reaching civilization may sit somewhere further along the road. Which means the silence might not be about the beginning of life at all. It might be about what happens after. 2 billion years of patience. A single number sits at the centre of this part of the story, and it is large enough to be difficult to feel. 2 billion! That is roughly how long Earth remained a world of microbes and nothing more. Life appeared relatively early in the planet's history, perhaps within the first few 100 million years after the surface cooled, but once it arrived it stayed small. For an almost incomprehensible stretch of time, every living thing on Earth was a single cell. Oceans teemed with bacteria and archaea. Microbial mats coated shallow sea floors. Photosynthetic organisms slowly began altering the atmosphere, releasing oxygen molecule by molecule into air that had previously contained almost none. But in all that time, nothing grew larger than a speck. No eyes formed, no limbs extended, no creature moved with intention across a landscape. The world was alive, thoroughly and abundantly alive, and yet by any measure we might use to look for civilizations from a distance, it would have appeared completely empty. That long plateau is one of the most quietly significant facts in the history of life on Earth. It tells us that biology, once established, does not automatically climb toward complexity. Evolution does not have a direction. It does not aim upward. It selects for whatever works in a given environment, and for 2 billion years what worked was simplicity. Single cells divided, adapted, colonized every niche available to them, from sunlit surfaces to deep ocean vents to cracks in ancient rock, and they did so with extraordinary success. There was no evolutionary pressure pushing toward multicellularity, no inherent advantage to being large. The world belonged to the small, and the small had no real reasons to change. What eventually broke that long stillness is still debated among biologists. But one event that appears to have been critical occurred somewhere around 2 billion years ago, possibly earlier. A single-celled organism engulfed another, not to digest it, but in a way that allowed both to survive. The engulfed cell over time became what we now call a mitochondria, in the structure inside complex cells that generates energy. This event, known as endosymbiosis, may have happened only once in the entire history of life on Earth. Every animal, every plant, every fungus alive today carries mitochondria, descended from that original partnership. If it truly occurred only once in 4 billion years of biology, then it may represent one of the rarest transitions life has ever made, a bottleneck so narrow that most planets with microbial oceans might never pass through it at all. The detail is small in scale, but enormous in consequence, because without that single merger complex, life as we know it could not exist. Mitochondria provide the energy budget that large multicelled organisms require. A bacterium can survive on very little, but a creature with tissues, organs, and a nervous system demands far more. Without the energy surplus that mitochondria provide, the leap to complexity may simply be impossible. Some researchers have argued that this is precisely where the Great Filter sits, not at the origin of life, not at the emergence of intelligence, but here at the quiet junction where one cell swallowed another, and the world eventually changed because of it. Even after endosymbiosis, multicellularity did not arrive immediately. It took hundreds of millions of years more before cells began cooperating in ways that produced organisms with differentiated tissues. The earliest fossils that may represent multicellular life, the Ediacaran biota, named after the Ediacara Hills in South Australia, where they were first identified in the 1940s, date to roughly 575 million years ago. These were strange soft-bodied organisms, many of them unlike anything alive today. Some resembled fronds, others looked like quilted discs or segmented ribbons pressed into ancient seafloor sediment. They left no shells, no bones, no hard parts at all. Their fossils survive only as impressions in fine-grained sandstone, faint textures that could easily be overlooked if you did not know what you were looking at. What the Ediacaran organisms tell us is that multicellularity, when it finally appeared, was tentative. These were not the ancestors of most modern animals. Many of them seem to represent evolutionary experiments that led nowhere, body plans that flourished briefly and then vanished without descendants. The transition to complex life was not a single confident leap, but a series of uncertain steps, many of which failed. On Earth, it took the better part of 1 billion years after endosymbiosis for anything resembling an animal to appear in the fossil record. That pace suggests the transition was neither easy nor inevitable. It suggests that the path from microbe to complex organism is littered with obstacles, and that most of them are invisible to us because the failures left no trace. Consider what this means for the silence of the galaxy. If microbial life is common, if it arises on many worlds where water and chemistry cooperate, then the universe may be full of planets that look biologically the way Earth did for its first 2 billion years. Oceans thick with bacteria, atmospheres slowly being reshaped by photosynthesis, but nothing more. No movement, no awareness, no signal that could ever cross the distance between stars. A telescope pointed at such a world might detect signs of biological chemistry in its atmosphere. Oxygen, methane, perhaps other gases that hint at living processes, but it would never detect civilization. From a distance, these planets would look alive but silent. They would contribute to the quiet that presses against every survey we have ever conducted. Some astrobiologists find this scenario the most likely explanation for the Fermi paradox. They argue that the filters are not dramatic, not nuclear wars or runaway technologies, but quiet biological bottlenecks that most worlds never cross. The origin of life may be common enough, but the leap to complexity may be so difficult that it has happened only a handful of times in the entire history of the galaxy. If that is true, then the silence we hear is not the echo of civilizations that destroyed themselves. It is the sound of worlds where biology never grew beyond the microscopic, where 2 billion years of patience stretched into 4 and then 8, and then the star itself aged and dimmed, and the oceans slowly boiled away, and nothing ever looked up from the surface to wonder why. That thought carries a particular kind of weight, because it means the Great Filter may not be about failure at all. It may simply be about probability, about steps so unlikely that time alone is not enough to guarantee them. And if the step from simple cells to complex life is one of those barriers, then every forest, every bird, every creature with eyes and limbs, the capacity to move through the world with purpose is the product of something extraordinarily rare. The complexity we take for granted may be the exception the universe almost never produces. And the long silence overhead may be the sound of all the worlds where patience was never rewarded with anything more. The accident that made us possible. Why should a brain, capable of asking questions about the stars, ever appear at all? It is a question that sounds almost philosophical, but the fossil record gives it a surprisingly concrete shape. For most of the time that complex life has existed on Earth, roughly the last 540 million years since the so-called Cambrian explosion filled the oceans with creatures bearing shells, eyes, and segmented bodies into intelligence of the kind that builds civilizations was nowhere to be found. Animals diversified into extraordinary forms. They colonized every environment the planet offered, from deep ocean trenches to mountain peaks, from tropical canopies to frozen tundra. They grew armored plates, venomous spines, wings capable of crossing continents, and jaws strong enough to crush bone. By every measure of biological success, the animal kingdom flourished. But none of it pointed towards technology. None of it required abstract thought, symbolic language, or the capacity to wonder about anything beyond the immediate demands of survival. Dinosaurs are the most striking illustration of this point, and they deserve a slow look because of what their story tells us about the relationship between time and intelligence. The earliest dinosaurs appeared roughly 230 million years ago during the Triassic period. Over the following 160 million years, they became the dominant land animals on Earth. They adapted to every climate zone, evolved into thousands of species ranged in size from creatures no larger than a chicken to animals that weighed more than 80 tons. Some were social, some cared for their young, some hunted in coordinated groups, suggesting at least a rudimentary capacity for communication and strategy. And yet across that entire span, a duration so long that it dwarfs the entire history of mammals, not a single lineage of dinosaurs developed anything resembling technology. No tools beyond claws and teeth, no structures beyond nests, no system for preserving knowledge across generations. 160 million years, and the closest thing to engineering was a well-constructed burrow. That fact alone should give us pause when we imagine civilizations arising on other worlds. Evolution does not trend toward intelligence. It trends toward whatever works, and for the vast majority of Earth's history, intelligence in our sense of the word was not what worked. Speed worked, size worked, camouflage, venom, thick hide, sharp senses. These were the strategies that filled ecological niches and kept lineages alive for millions of years. Big brains, by contrast, are akin to. They consume disproportionate amounts of energy. They require long developmental periods, extended parental care, and social structures complex enough to make that investment worthwhile. For most of evolutionary history, the cost of intelligence outweighed its benefits. The universe may be full of planets where complex life thrived for hundreds of millions of years without ever producing a single creature that could count to 10. What changed on Earth was not a gradual march toward awareness. It was a catastrophe. 66 million years ago, an asteroid roughly 10 to 12 kilometers in diameter struck what is now the Yucatan Peninsula in southeastern Mexico. The impact site, known as the Chicxulub crater, lies buried beneath layers of limestone and ocean sediment, but its dimensions have been mapped through gravity surveys and drill cores. The crater is approximately 180 kilometers wide and 20 kilometers deep, a scar so large it reshaped the geology of the entire region. The energy released on impact was equivalent to roughly 10 billion nuclear weapons detonating simultaneously. Dust and debris were thrown into the upper atmosphere, blocking sunlight for some months or possibly years. Temperatures plummeted. Photosynthesis collapsed. Food chains that had sustained the largest animals on the planet disintegrated within a geological instant. An estimated 75% of all species on Earth went extinct, including every non-avian dinosaur. It was the end of one world and the quiet, uncertain beginning of another. In the ecological vacuum left behind, mammals, small adaptable, and until then largely marginal, began to diversify. Over the following tens of millions of years, they filled niches that had been occupied by dinosaurs for ages. They grew larger, developed new body plans, spread across every continent. Primates appeared, and within that order a lineage emerged that favoured social living, dexterous hands, and increasingly large brains relative to body size. But even among primates, the path to technological intelligence was not straight. Dozens of primate species evolved and thrived without developing language art or tools more complex than a stick used to fish termites from a mound. Only one narrow branch, our own, eventually crossed the threshold into symbolic thought, cumulative culture, and the capacity to reshape the planet itself. The implication is difficult to soften. Intelligence, at least of the kind that wonders us about the silence of the stars, appears to have required a specific and unlikely sequence of events on Earth. Remove the asteroid and mammals might never have risen to prominence. Alter the climate shifts that shaped early hominin evolution in East Africa, and bipedalism, or enlarged brains, might never have been selected for. Change any one of a dozen variables in the last 66 million years, and there would be no radio telescopes, no space probes, no one sitting quietly under the night sky, asking where everybody else might be. The spark of technological intelligence did not emerge because the universe intended it. It emerged because a chain of accidents happened to fall in a particular order on one particular planet, and this chain could easily have broken at any link. This matters for the great filter, because it suggests that even on worlds rich with complex life, worlds with forests and oceans and creatures of extraordinary diversity, intelligence may almost never appear. The silence of the galaxy might not be about the absence of life. It might be about the absence of minds. Billions of planets might host biology far more elaborate than microbes' ecosystems, as rich and varied as the Cretaceous forests that dinosaurs once walked through, and none of them might ever produce a species capable of looking upward and asking a question. The filter in that case would not be biological death. It would be biological indifference evolution, simply finding no reason to build a mind that reaches for the stars because survival never required it. And if intelligence is that rare, then the question shifts. It is no longer only about why the universe is quiet. It becomes about what happens when, against all odds, something like us does appear, and whether we understand how unlikely our own existence truly is. The narrowing genetic studies conducted over the past few decades have revealed something about our species that is easy to overlook when you consider the 8 billion people alive today. Somewhere around 70,000 years ago, the total population of Homo sapiens may have dropped to as few as a few thousand breeding individuals. The evidence comes from the structure of our DNA itself, a surprising lack of genetic diversity compared to other great apes. Chimpanzees, whose total population is a fraction of ours, carry more genetic variation within their species than all of humanity combined. That pattern only makes sense if our ancestors passed through a severe bottleneck, a period in which the number of surviving humans shrank so dramatically that the genetic diversity of the entire species was compressed into a narrow thread. The cause remains debated. Some researchers point to the eruption of Mount Toba in Sumatra roughly 74,000 years ago, one of the largest volcanic events of the past 2 million years, which may have triggered a prolonged volcanic winter. Others suggest the bottleneck was driven by climate shifts, drought, or a combination of pressures that made survival on the East African landscape precarious in ways we cannot fully reconstruct. Whatever the cause, the outcome is the same. The species that would one day build telescopes and wonder about the stars very nearly did not survive at all. That bottleneck is worth sitting with for a moment because it reframes the entire story of human civilization. Everything that followed language, agriculture, writing, mathematics, industry, spaceflight, all of it rests on the survival of those few thousand individuals. If the population had dropped just slightly further, if one more season of drought had emptied one more valley, there would be no cities, no libraries, no radio signals leaking into space. Earth would still be a living planet rich with animals and ecosystems, but it would be a planet without questions. The silence of the galaxy would include us, and no one would be here to notice it. The margin between the existence of human civilization and its complete absence may have been astonishingly thin, and a few hundred people in the right place during the right season carrying enough genetic diversity to rebuild a species that had nearly vanished. Even after the bottleneck, the path forward was not assured. For tens of thousands of years, humans lived in small mobile groups, hunting, gathering, following the rhythms of seasons and animal migrations. They developed language, created art on cave walls in places like Lascaux in southern France and Sulawesi in Indonesia, and buried their dead with objects that suggest some awareness of meaning beyond the immediate. But they did not build permanent settlements. They did not farm. They did not accumulate the kind of surplus that allows populations to grow dense enough to specialize, innovate, and record what they learn. For the vast majority of our existence as a species, we lived in a way that would have been invisible from orbit. No roads, no structures, no light at night. If an alien civilization had surveyed Earth 40,000 years ago, with the best instruments imaginable, they might have detected the atmospheric signatures of the living planet, but they would have found no evidence of intelligence. We were here, but we were quiet. The transition to agriculture, which began independently in several regions roughly 10 to 12,000 years ago in the Fertile Crescent of modern-day Iraq and Syria, in the Yangtze River basin of China and Mesoamerica, changed that equation. For the first time, humans could stay in one place, produce food in surplus, and support populations large enough to develop division of labour. From that shift came villages, then towns, then cities. Writing appeared in Mesopotamia around 5,000 years ago initially, as a system for tracking grain stores and trade goods, and eventually became a tool for preserving stories, laws, and knowledge. Each of these steps compounded the last, and the pace of change began to accelerate in ways that no previous period of human history had seen. But each step also introduced new vulnerabilities. Settled populations were dependent on specific crops, specific water sources, specific trade routes. When those systems failed through drought, disease invasion, or internal collapse, civilizations did not simply slow down, they fell apart. The archaeological record is full with such collapses, and they are more common than popular history tends to acknowledge. The Akkadian Empire, often considered the first true empire in human history, flourished in Mesopotamia around 4,300 years ago and disintegrated within a few generations, likely under the stress of prolonged drought. The Indus Valley Civilization, which at its height supported perhaps 5 million people across hundreds of planned cities in what is now Pakistan and northwestern India, declined and fragmented around 3,500 years ago for reasons still not fully understood. The classic Maya, whose cities in the lowlands of present-day Guatemala and Mexico supported complex astronomy and mathematics and monumental architecture, experienced a broad collapse between the 8th and 10th centuries that left great urban centres abandoned to the jungle. In each case, the pattern is similar. A society rises, builds systems of remarkable sophistication, and then encounters limits it cannot overcome. The fall is rarely sudden. It is usually a slow unravelling, a fraying of the systems that held everything together, followed by fragmentation, migration, and silence. What these collapses share beyond their geographic and cultural diversity is a common lesson about the relationship between complexity and fragility. The more intricate a civilization becomes, the more dependent it is on the stability of its supporting systems. A simple hunter-gatherer band can relocate when the rains fail. A city of 50,000 cannot. A trading network that spans a continent can distribute resources with extraordinary efficiency, but when one node fails, the disruption cascades outward in ways that a simpler system would never experience. Complexity is powerful, but it is also brittle. And the more a civilization invests in complexity, the higher the cost when that complexity breaks. This is not merely a historical observation. It is a pattern that some researchers believe may be universal, a tendency built into the nature of civilizations themselves, wherever they arise. If complexity always carries the seeds of fragility, then the Great Filter may not be a single dramatic event. It may be a structural tendency, a quiet gravitational pull toward collapse that every rising civilization must eventually contend with. The ruins of Akkad and the empty plazas of Tikal may not just be chapters in human history. They may be small-scale echoes of something far larger, a pattern that repeats across the galaxy on worlds we will never visit, among species we will never meet, each one building toward a height it could not sustain. And if that pattern holds, then the question is not whether civilizations fall. It is whether any of them learn to catch themselves before the fall becomes final, the weight of what we built. How long does it take to go from carving symbols into wet clay to splitting the atom? On the scale of the universe, the answer is almost no time at all. Writing appeared in Mesopotamia roughly 5,000 years ago. The first controlled nuclear chain reaction took place in December 1942 beneath the bleachers of a disused football stadium at the University of Chicago, in a makeshift laboratory so secret that most of the university's own staff did not know it existed. Between those two moments, the reed stylus pressing cuneiform into a tablet, and the quiet click of a neutron counter confirming that a self-sustaining reaction had been achieved, lies the entire arc of recorded human civilization. 5,000 years, on a cosmic timeline that is less than a heartbeat, and within that heartbeat we went from a species that could barely feed itself through a single winter to one that could, if it chose, render the surface of its own planet uninhabitable in an afternoon. The acceleration is part of what makes the Great Filter so difficult to think about calmly. Each major technological leap has arrived faster than the one before it. Agriculture took thousands of years to spread across the globe. Industrialization took centuries. The digital revolution took decades. Artificial intelligence is reshaping economies and decision-making systems in what may be measured in years. Each leap compounds the power available to a civilization, but it also compounds the risk, because the capacity to destroy has scaled, alongside the capacity to create, and the two have never been separable. The same chemistry that produces fertilizer for crops produces explosives for warfare. The same physics that powers a city can flatten one. The same biology that cures disease can in principle engineer pathogens more lethal than anything nature has produced. Power, it seems, does not arrive in halves. It arrives whole, and what a civilization does with both sides of it determines whether the story continues. Nuclear weapons remain the most immediate illustration of this problem, not because they are the most likely source of extinction, but because they are the most concrete. At the peak of the Cold War, the combined arsenals of the United States and the Soviet Union contained more than 60,000 nuclear warheads, enough to destroy every major city on Earth several times over. The logic that governed their deployment was a doctrine called mutually assured destruction, a framework in which safety depended entirely on the certainty that any attack would result in the annihilation of both sides. It worked in the sense that no weapons were launched, but the margin of safety was thinner than most people realize. In September 1983, a Soviet early warning satellite reported that 5 American intercontinental missiles had been launched toward the Soviet Union. The officer on duty, Stanislav Petrov, judged the alert to be a system malfunction and chose not to escalate. He was right, the signal had been caused by sunlight reflecting off high-altitude clouds. If he had followed protocol, the Soviet response might have triggered a full exchange. The distance between civilization and silence in that moment was one man's judgment call in a room full of blinking screens. That incident is not unique. Declassified records from both American and Soviet archives reveal multiple occasions during the Cold War when miscommunication, technical failure, or simple human error brought the world closer to nuclear war than any official statement ever acknowledged. The Cuban Missile Crisis of 1962 is the most well-known, but there were other moments that never made headlines because the people involved chose restraint, or because luck intervened at the last possible second. The weapons from that era have not disappeared. Global stockpiles have been reduced since the Cold War's peak, but thousands of warheads remain active, maintained by multiple nations governed by systems that are only as reliable as the humans and technologies that operate them. The risk has changed shape, but it has not gone away. And nuclear weapons are only one thread in a widening fabric of existential risk. Climate change operates on a slower timescale, but with no less potential for civilizational disruption. The mechanisms are well understood. Greenhouse gases trap heat oceans, warm ice sheets, lose mass, weather patterns shift, but the consequences cascade in ways that are difficult to model with precision. Agricultural regions that feed billions may become unreliable. Coastal cities that house hundreds of millions may face inundation. Water sources that sustain entire nations may diminish. None of these outcomes would necessarily end the human species outright, but they could fracture the systems of trade governance and cooperation that modern civilization depends upon. And a civilization that fractures deeply enough may not recover in time to face the next challenge. Artificial intelligence introduces a different kind of uncertainty. Not the slow accumulation of physical damage, but the rapid redistribution of power and decision-making in ways that no previous technology has enabled. Systems capable of learning, adapting, and acting on their own are already being integrated into financial markets, military strategy, medical diagnosis, and scientific research. The benefits are real and in many cases profound. But the risks are not yet fully understood, in part because the systems themselves are evolving faster than the frameworks designed to govern them. A technology that outpaces the wisdom of the civilization that created it is not a new phenomenon. It has happened before with consequences that range from manageable to catastrophic. What is new is the speed, the scale, and the degree to which the consequences of failure could be irreversible. Each of these risks, nuclear, environmental, technological, can be discussed in isolation, but the deeper concern is their convergence. A civilization facing any one of them might adapt and survive. A civilization facing all of them simultaneously within the span of as few generations operates in a narrower corridor of safety than any that has come before. And if the pattern suggested by the silence of the galaxy holds, if civilizations elsewhere reached a similar threshold and did not pass through, then the corridor may be narrower still than we would like to believe. The question the silence poses is not whether these risks exist. We already know they do. The question is whether a species capable of building such power is also capable of carrying it without stumbling, and whether the answer to that question has ever anywhere been yes. What the silence might not mean, before we drift further into the weight of these questions, it is worth pausing to ask whether the silence of the galaxy means what we have been assuming it means. Because there is a version of this story in which the quiet sky is not a warning at all, in which it reflects not the failure of civilizations, but the limits of our own ability to look. That version deserves a fair hearing, and the honesty to sit with it for a moment, even if it does not resolve the unease entirely. The most straightforward objection is one of scale. The Milky Way contains somewhere between 200 and 400 billion stars. Our search for extraterrestrial intelligence, spanning roughly 6 decades of effort, has examined only a tiny fraction of them. The comparison that astronomers sometimes offer is useful here. Imagine standing on the shore of the Pacific Ocean, filling a single glass with seawater, and then concluding that the ocean contains no whales because you found none in your cup. That is, roughly speaking, the proportion of the galaxy we have sampled so far. SETI programs have scanned thousands of stars across limited frequency bands during limited windows of time. The absence of a signal in that narrow sample does not by itself prove that signals do not exist. It may simply mean we have not yet pointed our instruments in the right direction at the right moment. The search in statistical terms has barely begun. There is also the question of what we are looking for. Our detection methods are built around assumptions rooted in our own technology. We listen for radio waves because radio is how we first learned to broadcast across distances. We look for megastructures because engineering at that scale is what our own physics suggests an advanced civilization might attempt. But what if those assumptions are wrong? A civilization even a few centuries ahead of ours might communicate using methods we have not yet conceived encoded in particles. We do not monitor at frequencies we have not thought to scan or through mediums that our current instruments cannot detect. The analogy that appears in the scientific literature is not subtle. It would be like an ant colony attempting to detect the internet. The infrastructure is everywhere, but the ant has no framework for recognizing it. If advanced civilizations exist but operate on principles fundamentally different from our own, then the silence we perceive may not be silence at all. It may be a conversation happening in a language we have not yet learned to hear. A third objection concerns time. Civilizations, even if they are relatively common, might not overlap. Stars and planets endure for billions of years, but a technological civilization might broadcast detectable signals for only a few centuries or millennia before either falling silent or transitioning to communication methods that are invisible to outsiders. If that is the case, then the odds of two civilizations existing close enough in both space and time to detect one another become remarkably small. We might be living in a galaxy where hundreds of civilizations have risen and faded over the past several billion years, each one occupying its own brief window, none lasting long enough to notice the others. The silence in that interpretation is not evidence of absence. It is evidence of bad timing, a cosmic mismatch between the lifespans of civilizations and the distances between stars. Each of these objections carries weight and none of them can be dismissed easily. They remind us that the Fermi paradox is built partly on assumptions, and assumptions can be wrong. The silence may be telling us something profound about the fate of civilizations, or it may be telling us something mundane about the limits of our instruments and the narrowness of our search. Intellectual honesty requires holding both possibilities without collapsing prematurely into either one. And yet even after granting all of these objections their due, the discomfort does not fully dissolve. Because the question is not only whether we have failed to detect signals, it is whether we have failed to detect anything at all. If civilizations are common, even if their signals are brief, you might expect at least one of them, out of the billions of chances the galaxy has offered, to have expanded physically, to have built something large enough and durable enough to leave a trace that persists across millions of years. A structure orbiting a star, a pattern of resource extraction visible in the chemistry of a planetary system, an artifact drifting through interstellar space. The galaxy is old enough and large enough that even rare events should have produced at least one visible result. The fact that surveys of thousands of stars have found nothing definitively artificial is not conclusive, but it is not trivial either. It sits in the record like a quiet, persistent question that the objections soften but do not erase. It may be natural, it may be chance, it may be that the search has simply not yet reached the threshold where absence becomes meaningful. The discomfort is that we cannot be sure. And in that uncertainty lies the reason the great filter continues to press on us, even when the counter-arguments are strong. Because the stakes of being wrong are not symmetrical. If the silence is simply a matter of limited search, then there is no cause for alarm and we need only be patient. But if the silence reflects something real about the difficulty of survival, if civilizations genuinely do rise and quietly fade with a regularity that the galaxy has witnessed countless times, then patience alone will not protect us. We would need to act with a kind of care that our species has only rarely demonstrated, and the cost of assuming the optimistic interpretation if it turns out to be wrong would be measured not in data points, but in everything we are. The objections are real, the uncertainty is real, but so is the pattern that keeps surfacing beneath it, the strange persistent absence that every new survey confirms rather than resolves. And it is that pattern more than any single piece of evidence that draws us forward into the next part of the story, the ones who chose to stay quiet. What if the galaxy is not empty at all, but full of civilizations that have simply decided not to speak? The question sounds almost absurd at first, a conspiracy theory scaled up to the size of the cosmos, but it has been taken seriously by enough physicists and philosophers to deserve more than a passing glance. Because the silence of the universe admits more than one interpretation, and some of those interpretations do not require extinction at all. They only require caution. The idea takes several forms, each with its own internal logic, and each painting a different portrait of what the galaxy might actually look like if we could somehow see past our own limitations. The most well-known version is sometimes called the zoo hypothesis, a term coined by the radio astronomer John Ball in a 1973 paper. The premise is disarmingly simple. If one or more civilizations in the galaxy reached a level of advancement far beyond our own, they might have collectively agreed or individually decided not to interfere with younger species still developing on their own. Earth in this view would be something like a nature reserve. Observed, perhaps studied, but deliberately left alone so that its inhabitants could evolve without outside influence. The analogy to wildlife conservation is intentional. We set aside protected areas on our own planet precisely because we recognize that interference can damage the systems we wish to understand. A civilization with the power to cross interstellar distances might apply the same logic to emerging species choosing restraint over contact, patience over revelation. It is a generous interpretation and it carries a certain elegance, but it also raises a problem that its proponents have never fully resolved. For the zoo hypothesis to explain the total silence we observe every advanced civilization in the galaxy, without exception, exception would have to follow the same policy. Not most of them, all of them. A single defector, a single civilization curious or careless enough to make contact would be enough to break the silence. And the idea that universal consensus could be maintained across billions of stars and millions of years is, to put it gently, optimistic about the nature of intelligence in ways that our own history does not support. A darker variation emerged more recently, drawn in part from the Chinese science fiction novelist Liu Cixin's trilogy The Three-Body Problem, published between 2008 and 2010, in what has come to be called the Dark Forest Hypothesis. The galaxy is imagined not as a zoo, but as a forest at night, vast, dark, and filled with hunters. Every civilization is a potential threat to every other. Resources are finite. Trust between species separated by light years is impossible to establish. And the safest strategy in a universe where you cannot know whether a stranger is peaceful or predatory is to remain hidden. Broadcasting your location is not an invitation to friendship. It is a beacon for destruction. In this framework, the silence is not politeness. It is fear. Every civilization that survives long enough to understand the risks learns the same lesson: stay quiet, stay small, stay invisible. And the result is a galaxy that sounds empty, precisely because it is full of beings who have learned that making noise is the fastest way to die. The dark forest idea is compelling as narrative, and it captures something real about the logic of survival under uncertainty. But like the zoo hypothesis, it requires a level of universal behavior that is difficult to justify. It assumes that aggression or predation is the dominant strategy across all civilizations, and that no species ever finds safety in openness at alliance or simply being too far away to threaten anyone. It assumes a galaxy governed by a single game theoretic equilibrium, which may say more about our own anxieties than about the actual dynamics of interstellar life. There is a third possibility quieter than the others and in some ways more unsettling. Perhaps civilizations do not hide and do not perish. Perhaps they simply lose interest. A species that develops sufficiently advanced technology might eventually create internal worlds so rich, so absorbing, so perfectly tailored to the desires of its inhabitants, that the vast emptiness of outer space becomes irrelevant. Why spend millennia crossing the void between stars when you can build a reality indistinguishable from paradise inside the energy budget of a single planet? This idea, sometimes called the transcension hypothesis, as explored by the futurist John Smart, suggests that advanced civilizations do not expand outward. They collapse inward into computational substrates of extraordinary density exploring inner space rather than outer space. From the outside, a certain civilization would be invisible. Its energy use might be minimal, its physical footprint negligible, its interest in communicating with primitive radio broadcasting species precisely zero. The silence in this interpretation is not the sound of death or caution, it is the sound of satisfaction of a galaxy full of minds that found something better to do than explore. Each of these explanations offers a way to preserve the hope that we are not alone. Each one fills the silence with hidden company, turning absence into something more bearable, a choice, a strategy, a preference. And each one is in its own way plausible enough that it cannot be ruled out. But taken together, they share a common weakness. They all require that whatever is happening out there leaves no trace at all. No accidental signal, no stray artifact, no anomaly that breaks the pattern. And over billions of years across billions of stars, the probability that every civilization, whether hiding, watching, or dreaming, maintains perfect invisibility without a single exception, begins to feel like its own kind of silence. Not the silence of hidden company, but the silence of an explanation that almost works, and yet does not quite close the gap. The gap remains, and the quiet patient and indifferent remains with it, which brings us back to the possibility that the silence may be less about what others have chosen, and more about what they could not avoid, the structural tendencies that pull civilizations wherever they arise, toward a brightness that cannot sustain itself. Burning bright. The Roman Empire at its territorial peak around the year 117 TE, under Emperor Trajan, stretched from the grey coasts of Britain to the deserts of Mesopotamia, from the forests of Germania to the sand-coloured plains of North Africa. It encompassed an estimated 60 to 70 million people connected by more than 80,000 kilometres of roads, governed by a legal and administrative system, so sophisticated that its principles still echo through modern jurisprudence. Aqueducts carried fresh water across valleys. Cities boasted public baths, libraries, and amphitheatres that could seat tens of thousands. Trade networks moved grain from Egypt, silver from Spain, silk from the far reaches of Asia, along routes that functioned with a regularity that would not be matched in Europe for over 1,000 years. By nearly any metric available to the ancient world, Rome was a success on a scale that had never been achieved before. And yet within 3 centuries of that peak, the western half of the empire had fragmented beyond recognition, its cities shrinking, its roads deteriorating, its institutions dissolving into a patchwork of successor kingdoms that could not maintain what had been built. The fall was not a single event but a long erosion, a slow withdrawal of coherence from systems that had grown too large, too interconnected, and too dependent on conditions that could not hold. The pattern is not unique to Rome. It appears again and again across human history, in civilizations separated by thousands of years and thousands of kilometers, each one arriving at a similar arc through apparently independent means. The Khmer Empire, centered on the vast temple complex of Angkor in present-day Cambodia, sustained a population that may have reached 1 million people at its height in the 12th and 13th centuries, making it one of the largest urban areas in the pre-industrial world. Its engineers built a water management system of extraordinary ambition, with reservoirs, canals and channels designed to capture monsoon rains and distribute them across an agricultural landscape that fed the entire civilization. When that system faltered, stressed by shifts in monsoon patterns, compounded by deforestation and the silting of critical waterways, the consequences rippled outward through every layer of society. The temples remained, but the city around them emptied. The infrastructure that had sustained 1 million lives became a monument to what sustained systems look like when they can no longer sustain. What connects Rome and Angkor and the dozens of other civilizations that followed similar trajectories is not a shared culture or geography. It is a shared relationship with complexity. Each civilization grew by adding layers: administrative, technological, agricultural, military, and each layer brought benefits that made the next layer possible. But each layer also added fragility. A road network is only useful if it is maintained. An aqueduct only functions if its source remains clean and its stones remain intact. A trade route only delivers grain if the political stability that protects it holds firm. When one layer fails, the stress does not stay contained. It passes upward and outward, weakening adjacent systems, creating cascades that are difficult to arrest once they begin. The historian Joseph Tainter, in his 1988 study of societal collapse, argued that this dynamic is not accidental but intrinsic to the way complex societies operate. Societies invest in complexity to solve problems, but each new layer of complexity yields diminishing returns while increasing the cost of maintenance. Eventually, the cost of sustaining the system exceeds the benefits it provides, and collapse becomes not a failure of will, but a rational, if devastating, simplification. If Tainter's framework holds any truth beyond Earth, then the implications for the silence of the galaxy are considerable. A civilization that arises on a distant world might follow the same general arc, building systems of increasing sophistication, enjoying the benefits of each new layer, and then encountering the point at which complexity becomes its own burden. The specific details would differ. The crops would be different, the materials unfamiliar, the political structures shaped by biologies and histories we cannot imagine. But the underlying dynamic, the tension between the power that complexity provides and the fragility it introduces, might be universal. Not because alien civilizations would resemble ours in any surface way, but because the mathematics of interconnected systems may behave the same way regardless of who builds them. A network is a network, whether it carries Roman grain or alien energy, and networks past a certain density become vulnerable to cascading failure in ways that their builders rarely anticipate until the cascade has already begun. This is what some researchers mean when they speak of civilizations burning bright. The brightness is not just metaphorical, it is the observable intensity of a system operating at peak output, maximum trade, maximum energy consumption, maximum connectivity, maximum reach. From a distance it looks like triumph, from inside it feels like progress. But the brightness also marks the point of maximum fragility, the moment when the system is most dependent on everything working in concert and least able to absorb a shock to any one of its parts. A civilization at peak brightness is not at its strongest. It is at its most precarious, balanced on a web of dependencies so intricate that even its architects may not fully understand how it holds together. The question that lingers, and the one that the silence of the galaxy does not answer, is whether this tendency is escapable. Is collapse the inevitable price of complexity, or is it possible to build systems resilient enough to sustain brightness without succumbing to fragility on Earth we do not yet know? Every civilization that has reached peak complexity has eventually contracted, though the human species itself has survived those contractions and rebuilt, often on different foundations, often in different places. Whether that resilience scales, whether a planetary or interstellar civilization could manage the same trick, remains untested. And the silence overhead suggests, without confirming, that the test may be harder than the brightness makes it appear. Some fires burn long because they are fed carefully. Others burn long because they are small enough never to exhaust their fuel. The civilizations that rise and quietly fade may be the ones that confused brightness with endurance and discovered too late that the two are not the same. Whether we are capable of learning that distinction before it applies to us is a question the next part of this story begins to explore. The quiet choices. What if the force that undoes civilizations is not dramatic at all? It is tempting when thinking about existential risk to imagine the end arriving as a single catastrophic event. A nuclear exchange, an asteroid impact, a technological accident so severe that recovery becomes impossible. Those scenarios are vivid and they command attention precisely because they are sudden and total. But the historical record suggests that civilizations more often decline through an accumulation of quieter failures choices that seem rational. In-the-moment trade-offs that appear manageable at the time neglect, so incremental that no single generation recognizes it as the thing that will eventually bring the whole structure down. Collapse, when it comes, rarely announces itself. It arrives dressed as normalcy, as the slow narrowing of options that were once abundant, as the gradual acceptance of conditions that an earlier generation would have found alarming. Consider the way societies manage resources over long periods. The pattern is remarkably consistent across cultures and centuries. A civilization discovers a source of wealth, fertile soil, a fishery, a forest, a mineral deposit, and builds systems around extracting it. In the early phases, the resource seems limitless. Returns are high, effort is low, and the systems that depend on extraction expand rapidly. Cities grow, populations increase, institutions become more elaborate, more specialized, more dependent on the continued flow of that resource. But resources are not limitless. Soils erode when farmed without rest. Fisheries collapse when harvested beyond their capacity to regenerate. Forests once cleared alter rainfall patterns and destabilize the land they once held together. The decline is usually gradual, a few % less yield each decade and a slight increase in the effort required to extract the same return, and because it is gradual it rarely triggers the kind of alarm that would force a fundamental change in behavior. Each generation inherits a slightly diminished baseline and accepts it as normal. The phenomenon has a name in ecology. It is called shifting baseline syndrome, and it may be one of the most dangerous tendencies a civilization can possess, because it means that the very species capable of measuring decline is also capable of forgetting what was lost. On Earth, we can see this process at work in real time. The North Atlantic cod fishery, once one of the richest marine ecosystems in the world, sustained communities along the coasts of Canada and New England for centuries. By the mid-20th century, industrial trawling had increased yields to extraordinary levels, and the fishery was treated as an engine of economic growth that could be expanded indefinitely. Warnings from marine biologists that stocks were declining were acknowledged, but not acted upon with sufficient urgency because the short-term costs of reducing the catch seemed higher than the long-term costs of continuing. In 1992, the Canadian government imposed a moratorium on cod fishing after stocks had collapsed to roughly 1% of their historical levels. 30,000 people lost their livelihoods. The ecosystem has not fully recovered to this day, more than 3 decades later. The collapse was not caused by ignorance. The data existed. The warnings were issued. It was caused by a series of quiet choices, each one understandable in isolation, each one contributing to a trajectory that in aggregate proved irreversible within any human time frame. If this pattern spares, and there is reason to suspect it might, that then the great filter may not be a wall that civilizations crash into. It may be a slope they slide down so gradually that they do not realize they are falling until the ground is too far below to reach. The silence of the galaxy in this interpretation would not be the sound of explosions or wars or sudden catastrophes. It would be the sound of slow, compounding neglect civilizations that consumed their futures, one small decision at a time, each one too minor to trigger alarm, all of them together, sufficient to ensure that the story ended quietly rather than dramatically. The fossil record would not show a moment of destruction. It would show a long, gentle curve downward like a tide going out so slowly that the creatures on the shore never noticed the water was leaving. There is a psychological dimension to this that may be as important as the material one. Human beings, and perhaps any intelligent species shaped by evolution, are not well equipped to respond to threats that unfold slowly. Our cognitive architecture was shaped by environments where the most dangerous things were immediate. Predators, storms, rival groups, falling rocks. We are exquisitely attuned to sudden changes and poorly attuned to gradual ones. A temperature increase of 2 degrees over a century does not trigger the same alarm response as a predator appearing at the edge of a clearing, even though the former may ultimately be far more consequential. This mismatch between the pace of modern threats and the pace of our instinctive responses is not a flaw that education alone can correct. It is embedded in the way our brains process risk, and it may represent a kind of cognitive filter, a built-in limitation that makes intelligent species systematically underestimate the dangers that move slowly enough to avoid triggering fear. If that limitation is widespread, if any species that evolves intelligence through natural selection carries a similar bias toward the immediate, then the great filter may be in part a psychological phenomenon, not a lack of knowledge, but a structural inability to act on knowledge that describes threats too slow to feel urgent. Civilizations might understand intellectually that their trajectory is unsustainable. They might produce research, convene conferences, draft agreements, and issue warnings. And they might, despite all of that, continue on the same path, not because they are foolish, but because their deepest instincts are calibrated to a world where the most important threats were always the fastest ones. This is the kind of filter that does not announce itself. It does not arrive as a crisis, but as a condition. A permanent low-grade mismatch between the speed of danger and the speed of response. And a civilization living inside that mismatch might never recognize it as the thing that defines its fate, because recognizing it would require exactly the kind of long-term perception that the mismatch itself prevents. The question of whether we can overcome that limitation, whether awareness of the bias is enough to correct for it, is one that our own century may be in the process of answering, whether we are ready for the answer or not. What if we already passed? There is a way of reading the silence that does not lead to dread. It is not the most popular interpretation, and it does not make for the most gripping narrative, but it may be the most important one to sit with, because it changes everything about what the quiet sky means for us. The possibility is this: perhaps the great filter is not ahead of us at all. Perhaps it is behind us, buried deep in the chain of events that brought us from chemistry to consciousness, and we are already on the other side of it. If that is true, then the silence of this galaxy is not a warning about what is coming. It is an explanation of how extraordinarily unlikely it was that anything like us ever appeared in the first place. The stars are quiet, not because civilizations keep failing, but because almost none of them ever began. Return to the chain of transitions that this story has traced so far. The origin of life from non-living chemistry still unexplained, still unreplicated in any laboratory, possibly a singular event in the history of our planet. The emergence of complex cells through endosymbiosis, a merger that may have occurred exactly once in 4 billion years of biology. The leap from single-celled organisms to multicellular life, a transition so difficult that Earth waited 2 billion years for it, and most lineages never made it at all. The evolution of intelligence capable of technology, an outcome so unlikely that 160 million years of dinosaur dominance produced nothing even close to it. And it took a 10-kilometer asteroid to clear the stage for the lineage that eventually would. Each of these steps, viewed individually, looks improbable. Viewed together, the chain begins to look less like a ladder and more like a sequence of near miracles, each one contingent on the one before it, each one capable of failing permanently without any obvious mechanism to try again. If that reading is correct, then most planets in the galaxy, even those with liquid water-stable climates and rich chemistry, may never have crossed the first threshold. Life itself might be vanishingly rare. And on the small number of worlds where life did appear, it might have remained microbial for the entire lifespan of the star, never producing anything more complex than a mat of bacteria clinging to a warm rock. The silence in this view is not the aftermath of collapse. It is the sound of a universe where the conditions for complexity were met almost nowhere and the conditions for intelligence were met perhaps only here. There is a strange loneliness in that idea, but there is also relief. Because if the hardest filters are behind us, then the future is not sealed. The threats we face, nuclear weapons, climate disruption, technological mismanagement, are real, but they are not cosmic inevitabilities. They are problems, and problems can, at least in principle, be solved. The filter does not wait ahead like a wall. It sits behind us like a mountain range we have already crossed, visible only when we turn around and measure the distance. Some scientists have argued that we will not be able to determine whether the filter is behind us or ahead of us until we find evidence of life elsewhere. If a probe sent to Mars or Europa or Enceladus were to discover even a single living microbe, a cell unrelated to anything on Earth arising from an independent origin, it would mean that the first filter, the origin of life, is not as difficult as it might seem. That discovery, which many people imagine would be cause for celebration, would in fact carry a deeply unsettling implication. Because if life starts easily, then the filter that explains the silence must sit further up the chain. It would mean that whatever stops civilizations from filling the galaxy probably happens after life begins, after complexity appears, perhaps after intelligence itself arises. It would shift the weight of probability from the past to the future, from a filter we have already cleared to one we have not yet encountered. The more alive the galaxy turns out to be, the more dangerous our own position becomes. It is one of the rare cases in science where good news at one level becomes bad news at another. Conversely, if every probe we send to other worlds finds nothing, if Mars is sterile, if Europa's ocean is empty, if the chemical signatures of exoplanet atmospheres reveal no biology at all, then the case for a past filter strengthens. Each dead world would be another piece of evidence that life itself is the bottleneck, and that we have already squeezed through the narrowest part of the passage. The silence of the galaxy would become paradoxically a source of quiet reassurance. Not because the universe is friendly, but because its indifference is the very thing that makes our existence extraordinary. We would not be one civilization among many waiting for the axe to fall. We would be one of the few, perhaps the only, who made it through a gauntlet so severe that the galaxy is still empty because of it. Neither answer is available to us yet. We have not found life beyond Earth, and we have not proven its absence. The probes we have sent to Mars have returned ambiguous results, tantalizing chemistry, but nothing that definitively crosses the line into biology. Future missions to the icy moons of Jupiter and Saturn may change the picture entirely, or they may deepen the ambiguity. Until then, we exist in a state of suspension, unable to know whether the hardest part of our journey is behind us or still ahead, unable to calibrate our urgency, because the most important variable remains unmeasured. What we can do is hold both possibilities at once, without pretending that comfort resolves the question. If the filter is behind us, then we carry something rare and worth protecting. If the filter is ahead, then we face something difficult and worth preparing for. In either case, the response looks remarkably similar: a civilization that takes its survival seriously, that does not assume the future is guaranteed, that treats its own existence as contingent rather than inevitable. The silence does not tell us which story is true, but it tells us that the answer matters, and that the way we live in the uncertainty may be the most important thing about us. Whether the mountain is behind us or the cliff is ahead, the walk demands the same care. And the fact that we can see both possibilities, that we can weigh them, and to choose how to respond, may itself be the rarest thing in a galaxy that has produced more stars than any mind could count, but so far only one civilization capable of wondering what the count might mean: holding the spark. Every fire needs tending. The metaphor is old enough to feel worn, but it persists because it captures something precise about the relationship between intelligence and survival that more technical language tends to obscure. A fire left alone does not maintain itself. It consumes what is nearest flares when the wind shifts and dies when the fuel runs out. Sustaining it requires attention not once but continuously. The right amount of air, the right kind of wood, the patience to let it breathe without smothering it or letting it rage beyond the circle of stones that keep it contained. Intelligence, as it has appeared on Earth, behaves in much the same way. It is powerful, it is hungry, and it does not by its nature regulate itself. Whatever regulation exists must be built, maintained, and rebuilt every time conditions change. And conditions always change. The civilizations that have endured longest on Earth were not as a rule the most powerful. They were the most adaptive. The Aboriginal cultures of Australia sustained continuous habitation of a single continent for at least 65,000 years, a span so long that it dwarfs every other continuous cultural tradition by an order of magnitude. They managed landscapes through controlled burning, a practice so precise that early European settlers mistook the resulting parkland-like terrain for natural wilderness rather than the product of tens of thousands of years of careful stewardship. They did not build monumental architecture. They did not develop writing in the form that Eurasian civilizations would have recognized. But they maintained knowledge systems encoded in oral tradition, song, and ceremony that preserved ecological information across hundreds of generations with a fidelity that written records rarely match. Their survival was not a matter of luck. It was a matter of design, a set of cultural practices calibrated over millennia to the carrying capacity of the land they inhabited. They did not burn bright. They burned steadily, and the steadiness was what allowed them to endure. That example is not offered as a prescription. The world of 8 billion people connected by digital networks and powered by industrial energy systems cannot simply adopt the practices of a Pleistocene-era culture and expect them to translate. The scales are incommensurable and the challenges are different in kind, not just in degree. But the underlying principle that endurance requires a relationship with limits, that sustainability is not a constant constraint on progress, but a condition for its continuation, may be more transferable than it first appears. Because what the Aboriginal example demonstrates is that intelligence is capable of long-term survival when it organises itself around the recognition that resources are finite, that systems have thresholds, and that the cost of exceeding those thresholds is not measured in years, but in centuries and millennia. The question is whether a civilization operating at planetary scale can achieve the same recognition before exceeding the thresholds that matter most. The evidence so far is mixed. On one hand, humanity has demonstrated a remarkable capacity to respond to crises once they become undeniable. The Montreal Protocol of 1987, which phased out the production of chlorofluorocarbons, responsible for depleting the ozone layer, is often cited as an example of successful global cooperation in the face of an environmental threat. The science was clear, the political will was mobilized, and the policy worked. The ozone layer is now slowly recovering decades ahead of the most pessimistic projections. The smallpox eradication campaign of the 20th century, coordinated by the World Health Organization and completed in 1980, eliminated a disease that had killed an estimated 300 million people in the 20th century alone. These are not trivial achievements. They demonstrate that the species is capable of identifying a threat, coordinating across borders and ideologies, and acting decisively enough to change the outcome. The capacity for collective survival is not theoretical. It has been exercised and has succeeded. On the other hand, the threats that remain unresolved are the ones that move slowly, distribute their costs unevenly, and require sustained effort over timescales that exceed the attention span of political systems designed to operate in cycles of 4 or 5 years. Climate change is the most prominent example, but it is not the only one. Biodiversity loss, soil degradation, antibiotic resistance, the proliferation of nuclear materials. Each of these represents a challenge that is well understood scientifically and poorly managed politically, not because the knowledge is absent, but because the structures of decision-making are misaligned with the pace and scale of the problem. The fire is burning unevenly, and the institutions responsible for tending it were built for a different kind of flame. This misalignment may be the most concrete form the Great Filter takes in our own time. Not a sudden catastrophe, but a persistent gap between the speed of emerging risks and the speed of collective response. A civilization that can solve problems, it can see clearly a hole in the ozone, a virus with a known genome, but struggles with problems that unfold across decades, affect different populations at different rates, and require sacrifices whose benefits will not be visible for generations. If that gap is a feature of intelligence itself, if any species that evolves through natural selection will tend to prioritize the immediate over the systemic, then the filter is not an event, but a condition. It's the distance between knowing what needs to be done and actually doing it, multiplied across every generation that inherits the consequences of the generation before. And yet the same intelligence that produces this gap also produces the awareness of it. We can study our own cognitive biases. We can design institutions that counterbalance short-term thinking. We can build monitoring systems that make slow-moving threats visible before they become irreversible. We can, though, We have not yet consistently chosen to structure our economies and governance systems around the principle that sustainability is not optional, but foundational. The tools exist. The knowledge exists. What remains uncertain is whether the will to use them can be sustained long enough across enough of the species to close the gap before the gap closes us. This is where the story returns to the silence, because the silence does not tell us whether the gap can be closed. It only tells us that so far the galaxy offers no evidence that anyone else has managed it. That absence is not proof of impossibility. It may simply reflect the rarity of the attempt or the difficulty of sustaining it across the timescales that matter. But it adds weight to the question, and the weight is not easily set aside. Because if we are one of the few civilizations to have reached this point, this narrow, precarious window where the risks are visible and the tools are available, but the outcome is not yet determined, then the choices we make in this window are not just consequential for us. They may be consequential for the question of whether intelligence anywhere can learn to hold its own fire without being consumed by it. The spark is in our hands. It has always been fragile. The only thing that has changed is that we now know it, and knowing for all its discomfort is the one advantage that no previous generation and perhaps no other civilization has ever fully possessed. What we do with that knowledge is the chapter that has not yet been written. A small planet under a silent sky. How far does a radio signal travel before it becomes indistinguishable from noise? The answer depends on the strength of the transmission, the sensitivity of the receiver, and the distance between them. But for Earth's unintentional broadcasts, the television signals the radar, pulses the accumulated electromagnetic chatter of a century of technology. The practical range is surprisingly short. Our signals have been expanding outward at the speed of light since the early 20th century, forming a sphere of radio emissions roughly 200 light-years in diameter. That sounds impressive until you compare it to the scale of the galaxy. The Milky Way is approximately 100,000 light-years across. Our radio bubble, the sum total of everything we have ever broadcast, occupies less than 1/1,000,000th of 1% of the galaxy's volume. And even within that bubble, the signals are faint, weakened by distance, scattered by interstellar dust, blurred by the background hum of the cosmos itself. A civilization on the far side of the galaxy, even one with instruments vastly more sensitive than our own, would have no way of knowing we exist. We are, for all practical purposes, still invisible. The silence we hear when we listen to the stars may be precisely what any civilization at our stage sounds like from the outside. A world that is alive with noise on its surface, but utterly silent to anyone more than a few hundred light-years away. That detail reframes the question in a way that is worth holding for a moment. We speak of the silence of the universe as though it were a settled verdict, an absence that demands explanation, a void that presses down with the weight of implication. And in a sense it is. The surveys we have conducted, the frequencies we have scanned, the stars we have examined for anomalies, all of these have returned results consistent with a galaxy that contains no obvious technological signatures apart from our own. But the conclusion we draw from that silence depends entirely on how much weight we are willing to place on a search that has by its own admission barely started. We have listened for decades. The galaxy has existed for billions of years. The mismatch between those timescales is so vast that drawing firm conclusions from the current data is less like reading a book and more like reading a single letter on a single page and trying to guess the plot. This is not an argument for complacency. The silence, even if it is partly an artifact of our limited search, still carries information. It tells us that no civilization in our neighbourhood has made itself unmistakably visible. No Dyson spheres blocking starlight within a few thousand light-years. No self-replicating probes arriving in our solar system. No signals so powerful that even our young instruments could not miss them. That local absence is real, and it narrows the range of possibilities in ways that matter. But it does not close the question. It leaves us in a space that is uncomfortable precisely because it is unresolved, a space where the silence could mean almost anything, and where the meaning we assign to it says as much about us as it does about the galaxy. What the silence does more than anything else is illuminate the value of what we have. If intelligence is rare, whether because the filters are behind us or because they lie ahead, then every institution that preserves knowledge Every policy that reduces existential risk, every act of cooperation that strengthens the systems on which survival depends, carries a weight that extends far beyond its immediate context. We are not just managing a civilization. We may be tending the only fire in a very large darkness. That thought is not comfortable, but it is clarifying in a way that comfort rarely achieves. It strips away the assumption that survival is someone else's responsibility, that the future will take care of itself, that intelligence is durable simply because it exists. It replaces those assumptions with something harder and more honest, the recognition that everything we value is contingent, that the chain of events that produced us could have broken at any point, and that the chain can still break if we are not careful with what remains. There is a particular quality to the night sky that changes once you have spent time with these questions. The stars do not look different. They are the same points of light that humans have watched for tens of thousands of years, the same patterns that our ancestors traced into constellations and wove into stories about gods and seasons and the passage of time. But the spaces between them feel different. The darkness is not just distance. It is possibility and absence held together, a canvas that may be empty, or may be full of things we cannot yet perceive, and we have no way of knowing which, until we learn to see more clearly. The silence is still there, as steady as it has always been, but it no longer feels like a wall. It feels like an open question, one that we are still in the process of answering, not with telescopes and equations alone, but with the way we choose to live on the one world where the question can still be asked. Perhaps one day the silence will break. A signal will arrive from a direction no one expected, carrying information in a form that takes years to decode. Or a probe ancient and weathered by the radiation of interstellar space will drift into our solar system and settle into an orbit that cannot be explained by gravity alone. Or we will find beneath the ice of a distant moon the chemical traces of a biology that arose independently from our own, not intelligence, not civilization, but life. Simple and unmistakable proof that the first filter is not as hard as we feared, and that the universe is capable of crossing that line more than once. Any of these discoveries would change the story. Each one would rewrite our understanding of where we stand and what the silence means. But until that day comes, we are left with what we have: a small planet, a fragile civilization, of a sky full of stars that do not answer when we call. And maybe that is enough. Not enough to resolve the question, but enough to know that the question matters. Enough to understand that survival is not guaranteed, and that the absence of guarantees is not a reason to despair, but a reason to be deliberate. Enough to recognize that the spark of intelligence, however it arrived, however improbable its origins, is here now in our hands, and that what we do with it, the care we show, the risks we manage, the patience we cultivate, may determine whether the silence of the galaxy is permanent or whether it was only ever the quiet before a voice finally learned to carry across the dark. The story is not finished. It has only reached the part where we decide what kind of story it will be. It began with a question asked over lunch in the New Mexico desert 76 years ago by a man who'd been thinking about stars and numbers and the strange fact that nobody seemed to be out there. 4 words, whereas everybody spoken casually between bites of food and never fully answered since. We have carried those 4 words through the whole of this evening, turning them over like a stone found on a path, examining them from one angle and then another. The stone has not changed. It is still smooth, still opaque, still heavier than it looks. But perhaps we hold it a little differently now. Perhaps we feel more than we did at the start, how much silence can weigh when you stop to listen to it, not as emptiness, but as the accumulated quiet of billions of years and billions of worlds, where something might have spoken and for reasons we cannot yet name, did not. We have not solved anything tonight. That is worth saying plainly, because the mind has a habit of wanting resolution, of searching for the sentence that ties the threads together and allows the story to rest. But this story does not rest. The silence of the galaxy is not a puzzle with a missing piece that once found will make the picture whole. It is more like a landscape seen through fog shapes that almost resolve outlines that suggest structure but shift when you step closer. We trace the chain of transitions that brought life from chemistry to consciousness on one small planet. We sat with the long patience of microbial oceans, the unlikely accident that cleared the way for minds like ours, the pattern of civilizations that built extraordinary things and then quietly let them go. We considered the possibility that the hardest barriers are behind us and the possibility that they are not. And at every turn the honest answer remained the same: we do not know. We do not know if life is common or rare. We do not know if intelligence is a fluke or a tendency. We do not know whether the silence means we are early or alone, or simply not listening in the right way. And perhaps that uncertainty is not a failure of the inquiry, but its truest finding. The universe does not owe us clarity. It offers evidence in fragments, a fossil pressed into ancient sandstone, a radio dish returning static, a genetic bottleneck written into the DNA of every person alive, and leaves us to arrange the fragments as best we can, knowing that the arrangement is provisional, that new pieces may arrive tomorrow or never, and that the spaces between the pieces are as much a part of the picture as the pieces themselves. There is one question that surfaced near the end of this journey and has not quite settled. If intelligence is fragile, if the spark that allows a species to wander about the stars is also the spark that gives it the power to extinguish itself, then what does it mean that we are here now? Aware of both the fragility and the power, holding them together in the same hands. It is not a question that needs answering tonight. It's the kind of question that can sit quietly beside you, asking nothing, requiring nothing, simply present the way a candle flame is present in a still room, neither demanding attention nor disappearing when you look away. And now the evening has done what it came to do. The stars are still overhead, whether you can see them from where you are or not. The silence is still there, vast and patient and unthreatening. The way deep water is unthreatening is when you are not trying to cross it, but only resting at its edge. Whatever questions followed you here can stay or go as they please. They will not be smaller in the morning, but they may feel lighter the way heavy things sometimes do, after you have carried them long enough to forget they were ever difficult to hold. Let your breathing slow, traveller. Let the quiet fold itself around you, not the silence of the galaxy, which belongs to distances too large to feel, but the smaller quiet of this room, this moment, this particular night in which you happen to exist on a planet that happens to be alive in a universe that for now has offered no proof that anything like you has ever happened before. That is not a burden. It is simply where the story has reached so far, and the story, as we said at the beginning, is not finished. It has only paused the way all things pause when the night comes in and the mind drifts toward rest. Let it pause, let it hold. Sleep will carry you from here.